So I just, it's like a more stereotype. Each MBTI type personality type that we react to behave the programmer. The MTJs, I can't believe this is the worst day of my life. I just finished second of the world programming championship.
Did you take the MBTI thing?
Yeah, I don't know if I took a good one, so I think.
Sorry?
Don't know if I took a good one.
A good one. What do you mean by good ones? They're all good.
Are they all good?
They're all good. It's just that certain types kind of lend themselves more to computer science and math, and other types lend to other types of the area of your study. All right. So it looks like we are good here. I just need to let people in. All right, so we got 3 so far. Okay, got one. All right. And I have to change my glasses. The privilege of getting older, where one pair of glasses is not enough. Right. I got everybody in. And so I will talk about the solution of the midterm or exam 2, but not in the lecture because we are kind of pressed for time. So I will make a recording that talks about the solution of exam 2. And obviously I can only talk about a particular version of exam 2. There are many, many versions of exam 2. They are all equivalent, with similar questions. So I can use one as an explanation. So other than that, we are now proceeding to talk about the stack. So our focus today is to talk about how we call a subroutine and how we return from a subroutine from the perspective of assembly language programming. So are we good with that? Are we ready to move on and talk about calling and returning from calling a subroutine and returning from the subroutine? Yes. Okay. All right. So let's go ahead and talk about that stuff. And before we move any further, what we are talking about today, we're calling and returning from subroutine. There's a module, and hopefully some people, I'm hoping that everybody got a chance to read it before class. So we'll see. I'm just going to open it as a new tab. There we go. All right. So the way we start this is to describe, what happens when you run this program in C. So this is a sample program. It has line number, so it's easy for me to refer to each line. Excuse me. Are there any questions about this program? I'm hoping that you guys are all understanding how useless, how utterly useless this program is. Right? So the only purpose of this entire program is to illustrate calling and return and how it may be done using assembly language. Okay, so if I were to describe the path of execution, the program is going to start with main. Okay, because every C program starts with the main function, and then it's going to get to line 007. Okay, and then that's going to call function f. Then we get to line 2, which is the beginning of the function f. Function f has nothing to do, so it returns right away. So when function f returns from the first call, where does it return to? I want you guys to tell me that. Which line does function f return to after we called it the first time? Does it return to line 7 or does it return to line 8? It's returned to line 8 because we are done with line 7. If we are to return to line 7, we're going to call function f again, which turns it into an infinite loop, right? So it returns to line 8. So we will go like, okay, so what is the whole point? Well, on line 8, we call f again. So control will pass to line 2 again. And then when we're done with function f, because the function f has nothing to do, where do we return to this time? we return to line 9, that is correct. Okay, at which point the main is going to return and the whole program is done. Okay, so from this description, it would appear to me that calling a subroutine can be done with a JMPI because we know exactly where we need to go. Does that make sense? In other words, on line 7, somehow we're going to involve at least a JMPI to the entry point of function f to get to the subroutine that they're calling. Okay, and the same thing on line 8. Okay, when we get to line 8, same deal. Okay, some kind of JMPI f instruction is going to get us to the entry point of the subroutine. And we already know JMPI really well. Okay, you specify where you want to continue execution as an immediate operand, which basically means it has to be a value that is resolvable at assembly time. Is that okay? Okay, so if I refer to certain values as quote unquote resolvable at compile time or assemble time, it's an implication that there are values that you cannot determine at assemble time. Does that make sense? Okay, so that would correspond to where we are supposed to go back to. Okay, because the first time we call f, remember f is going to line 2, f is starting to line 2, and then it's supposed to return to line 8 because we don't want to return to line 7. Right? The second time we call f, it's supposed to return to line 9. It's like, oh, so that means the return mechanism cannot be using a JMPI because where it's supposed to go back to continue execution in the caller is not fixed. It is not static. Okay, so let's let that sink in a little bit, okay? Does everybody understand what I just said? You cannot use a JMPI to return to the caller because where you need to go back to continue execution cannot be determined at assembly time. All right. So if that is the case, what are we going to do? Well, it's not too bad of a deal. I mean, all you have to do is to say the caller, which is main in this case, is going to be responsible to help the callee, which is function f, to remember where it has to go back to in order to continue execution in the caller. So something in the processor has to remember this. It has to remember, where am I supposed to go back to? Main will have to put something into somewhere in the processor so that the callee, when it's done with what it needs to do, will know, oh yeah, we need to go back to that location. Does that make sense? Okay, so what we'll do next is to talk about something, we'll digress to something that does not seem to relate to the problem that we have at hand here. In other words, what we're going to do is we are going to take a quick digression to talk about the stack. So if you have not taken CISP310, which is data structure, don't worry, okay? Because the concept of a stack is relatively simple. The implementation only requires that you understand pointers. So are we okay with pointers? I certainly hope so, because CISP360 is a prerequisite of this class. And it is also why CISP360 is a prerequisite of this class, is because we need to use pointers. All right, so we're going to talk about the stack. So let me zoom in a little bit, because this way you guys can read the content a little bit better. So a stack is also usually known as a LIFO, which means last in, first out. Okay. So in computer science and also in real life, there are mainly two ways to organize things in terms of how we put things into storage and how we retrieve things out of storage. The first one is actually not last in, first out. Most of the time, we want first in, first out, or FIFO. Okay, but last in, first out has its importance as well in computer science in general. So, okay, let's just say that you're going to Safeway, okay, and you're ready to check out. So the queue that you have to form in order to check out, is it using last in, first out, or is it using first in, first out? You would hope it's first in, first out. It's actually last. Okay, so next, okay, you're loading up a U-Haul truck, you're helping a friend to move, or you are moving because you're transferring to a four-year university that is not local. So you're loading up a U-Haul truck. So, and is the ordering of things, of how you load into the truck and how you retrieve things from the truck, is that first in, first out, or is it last in, first out? It is last in, first out, right? That last thing that you push into the truck and quickly slam the tailgate is going to be the first thing that fall out of the truck when you open up the tailgate, right? You open the tailgate, it's like things just kind of slide out of it. And the first thing that slides out is the very last thing that you push into the truck and slam the tailgate. Does that make sense? Okay, so it looks like we do understand, just intuitively what is last in, first out versus what is first in, first out. Are we good so far? Okay. So the next thing we need to do is to create the data structure to handle this last in, first out ordering of putting things in and retrieving things. Is that okay? So that's the objective. But in order to do that, you don't have to worry about, oh, is Tech going to talk about linked list or anything like that? Well, the answer is not yet. So we'll get to linked list, okay, when we talk about structures later on. But right now, we don't need to use a link. All we need are these three definitions here. So we are looking at a pound defined because I'm an old school C programmer. So I'm defining a macro called stack size, which is 32. But if you are a C++ purist and you say, oh, my professor said do not use pound define, fine. It's const unsigned stack size equals to 32. Okay, meaning exactly the same thing. It is just a constant. Okay. Line 2, we are declaring an array of 8-bit unsigned integers. That's what stack is. So stack as a global variable is nothing more than just an array, in this case 32 bytes, of unsigned 8-bit integers. Is that okay so far? I hope there are no super foreign concepts up to this point. We good? All right. So, and then the last one is the stack pointer. That's what SP is representing. It is a stack pointer. The stack pointer has a fairly simple type as well. It is a pointer to an unsigned 8-bit integer. That's all it is. So these three things, the first one is not even that important. Okay. So when you look at stack size, all it is really trying to do is to say, oh, we're going to have this many bytes on the stack. You can make it larger, you can make it smaller. It is not super important in this discussion, but I do need to make it a certain number. So then the next question is, okay, so in TTP, we assume the stack is from location 255 to the last byte available after the program takes up space. So let's just focus on this sentence right now. So in TTP, does anyone remember how many bits do we allocate to the address port of RAM? Let me rephrase that question. We know that sometimes the program counter can connect to the address port or the A port of RAM. So how many bits, what is the width of the program counter?
Oh, I was gonna say 8.
It is 8-bit, okay? Almost every single register is 8-bit wide, except for the flags register, because we only have 5 flags to store. Why waste your 3 bits? And then the other register that is also not 8-bit wide is the microcode pointer. The microcode pointer has 12 bits. Every other register, the 4 software accessible registers, A, B, C, and D, those are all 8-bit wide. The program counter is 8-bit wide. So those are the more important registers that we need to think about in today's life. Okay, so with 8-bit as the width of the register, Can someone tell me what is the largest unsigned integer that you can store? Let me ask that question again. As an 8-bit register, what is the largest unsigned integer that it can store? 255. It is because it is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. You add up all of those powers of 2, you get 255. So in this case, I'm merely talking about the very last addressable location in RAM, all the way down to the last byte, okay? That is not, okay, I shouldn't, let me rephrase that. Down to the byte next to the last byte of the code of your program. Okay, do you guys understand what I just said? Nope, okay. So when you use the assembler will give you a RAM file. And then you use that to load it into RAM. Is that correct? But the RAM file does not load and change every single location in RAM. It only loads up to what the program really needs. Is that okay? And that is what I'm referring to here. So if your program, according to the assembler, is going to use, I don't know, let's say 47 bytes, okay? So it's going to take up location 0 to location 46 in RAM. That means location 47 all the way up to location 255 will be considered the stack. Are we still doing okay so far in terms of where the stack is when we run a program in TDP? Your program starts from low memory location up to a certain point, depending on the complexity of your program. From the next byte that is available in RAM, all the way to the last byte in RAM, that would be your stack. Are we still doing okay so far? Okay, you first and then you, go ahead.
So does that mean on the stack, will we start at position 255 and then it kind of marches down 254, 253, or?
That's the way. So there are, okay, so you're asking a question that has two components in it. The first component is what is the region that we consider the stack? So the region that we consider is the stack is ranging from the location right next to the last byte that your program code actually uses all the way up to location 255. That would be the region. In other words, that would correspond to, okay, right there, how we allocate the stack. In other words, what bytes are available to use as the stack. But the other question that is implicit in what you asked is how do we utilize those locations? And in that case, you are correct. We start to use the highest location first, and then the next highest location, and so on. So that is correct. So you're correct in both cases, but there are actually two components to what you asked. Go ahead.
I was just going to ask, so it's going from the block right after the program goes to location 255. I just, the wording made it seem a little.
Okay, I can illustrate with an example.
Whenever you answer this question.
Okay, but I think more other students may have questions here, so I'm going to use an example. Okay, yeah, go ahead.
Does it just go to like
What if there's nothing in?
the last part of 55? There's nothing assigned to it from the stack? Does it just like?
That's kind of the whole point.
Does it pass it? Or does it just start to where there is?
Okay, so let me try to illustrate that using this program. So this is a program I cannot even remember. Oh, right, this is the program that finds the largest integer within register A, B, and C, and then store it to register D or something like that, right? Okay, so we'll just use this as an example. So we go to the RAM file. The RAM file, you can download it, right? So you just download the RAM file. We did that before, but I'm gonna do again. So we'll call this find max3 again in the temp folder. Okay, so we just replace it. And then I have to run logic sim. So this wasn't exactly what I planned to do in today's lecture, but it works too. So we'll go ahead and say, bring up our processor. All right, so when we just take a look at the content of RAM, okay, without loading anything first, okay, so this window will show you the entire content of RAM at this point. So how do we know this is close to the entire RAM? Not entirely yet. So I need to make it a little bit larger so it does show you all the locations in RAM. There we go. So the reason why I know this is showing all the content is because the last row starts at location F0 as a hexadecimal number. So when you count the number of bytes on that row, this would be F0, F1, and the last one is going to be FF. FF in hexadecimal is 255, which is the end of RAM. So let's go ahead and load the content into this RAM here. Okay. So we'll I think, oh, I don't have to close it, but it's okay to close it too. So we'll go to the temp folder and load find max3.csv, I believe. So now we have some content in it, and I go back to edit content. It is possible that this is actually part of the program, but it's not. Okay. So in this case, the program, this is the first byte that is available to be used as the stack. Everything before is part of the program, but starting at this location and after all the way up to location FF would belong to the stack. That is a region of RAM that is going to be used as the stack. So far, in terms of how we allocate or which part of RAM is considered the stack. All right, okay. So let's go back to the notes. And I cannot remember where it's right here. Okay, there we go. We also have to designate a register to be the stack pointer. For the rest of not only this discussion, for the rest of this entire semester, we are going to say, hey, register D, your new job is the stack pointer. So register D now has a special purpose, being the stack pointer of the processor. Is that okay? If anyone is asking or thinking, but why not register A or register B or register C? The answer is really simple, because it is an arbitrary choice on my part to designate register D as the stack pointer. Right? Register D does not have any superpower. It has the same power. It has the very same abilities as any one of the 4 registers. It is by convention that I specify register D as the stack pointer. Are we do okay so far with that concept? So when you see SP as a variable throughout this code here, it is equivalent to our register D. Question?
Sorry. So when you say location D, when you when you put it into the RAM, it just looked like it was started from like an X available hex. So I don't know if I'm misunderstanding. What do you mean from 255?
This is location 255. Everything from here all the way up to here is now considered a part of the stack.
And it moves backwards.
We're not quite there yet. Okay, so the other question was a little bit ahead of the discussion. So we are only interested in knowing which part of RAM is the stack. Okay, all right. All right, so getting back to the notes here. So to facilitate efficient use of instructions, a stack grows down instead of up. So the question is, what do you mean by growing down? Okay, so I can explain that. The best way to explain it is to basically give you the 2 lines of code in C that is equivalent to storing something on a stack. So let's just say that you have a value X, okay? So in this case, X can be a constant, can be something that is computed, can be an expression, I don't care what it is. But you want to store an unsigned 8-bit number on the stack. This is how we do it, okay? We decrement the stack pointer, and then we store X as a value to the location we ran that the stack pointer is pointing to. You do okay so far? Yes.
I was just gonna say, would there be an issue with reversing those? Because if you start out at like 255.
We'll worry about the initialization of the stack pointer later on.
Okay,
But we are just saying that, at any point, okay, if you want to store something on the stack, this is how we store an unsigned 8-bit integer on the stack. So that's a good question, but we are not too worried about the initialization of the stack pointer at this point.
So I've heard in my 400 class right now, like he was basically saying, then you declare a variable that goes on the stack.
That would be, okay, so we are gonna relate to those concepts, but not today. So when we get to where we store the local variables and where the parameters are, then, that discussion will become relevant, but not today. Okay, so very good. Okay, so it's good to be able to kind of relate concepts from different classes, because what this class is doing, at least in your case, is to give you an X-ray vision into how programs work in not only CISP400, but also CISP360, CISP430, and so on. Yep.
Yeah, because he was like, the stack grows downward and the heap grows up. And I don't know what that means, but I don't think it was.
Okay, so we're not going to have a heap, okay, because we do not have dynamically allocated memory in this case, because we only have 255 bytes altogether. That's combining the program, everything that you need to store as local variables, and a whole bunch of other stuff that we need to track on the stack. So we don't have a heap, so to speak, in this class. All right, so this is how to store something. So that means we first decrement the stack pointer, we subtract 1 from the stack pointer, and then we store the value that we want to store, we want to save, to the location that the stack pointer is pointing to. Do we have any questions about those 2 lines of code, just in terms of what kind of operation is happening? Don't have any questions? Yep, go ahead.
So you're saying like the stack pointer is moving down?
Yes. In terms of, so we have to be very clear what is up and what is down. It is moving down in the sense that down means lower memory locations. So in that sense, yes, it is moving down. Yes.
And again, the stack itself is like 64 or that's the size of the stack itself. Can you scroll up?
Stack size.
Yeah, the stack size itself is like 64.
It doesn't matter. I mean, that's just telling you what is the capacity of the stack, but it doesn't dictate how we use the stack. It doesn't have to be 32. If you want to make it 512, so be it.
So in this example, so the first part is 255. And the next one is at
No, not this one. Okay, so there are 2 things going on. One is the actual C code to illustrate, how we use a stack, how we use a stack pointer to manage things that we store and how we retrieve things from the stack. So that's one thing, which is completely written in C. The other concept, which eventually we have to do, is to map these concepts to what we can do with the TTP. So we are not quite ready to do the second part yet. We're still doing the first part, which means we're only looking at C code to understand what is the stack, how do we store something on the stack, and how do we retrieve something from the stack. So right now we're only looking at things from the C perspective and not quite translating that into TTP stuff yet. All right, are we okay so far? Yep.
From 50 to 255, you put it on 50 and then 51 and then 52. And then your pointer goes from 52 to 51, 50.
No, I'll give you some examples later on and that will illustrate what we are dealing with. All right. So once again, we have, these two lines of code to store something on the stack. So now when it's time to retrieve something from the stack, these two lines of code is how we retrieve something from the stack. What we do is this type of thing has to be a variable or at least there's some place that I can store something. So when we retrieve something from the stack, we just look at the stack pointer as it is right now and ask, what are you pointing at in red? And then the content at the location that the stack pointer is pointing to is the content that we're retrieving from the stack. And it is now stored in some X variable. Remember, this is C code, okay? And then the next line is we now have to post increment the stack pointer. Because once you retrieve something from the stack, it is quote unquote not on the stack anymore. Is that okay? Yep.
Can we retrieve something from the middle of the stack without losing?
We cannot. So with a stack, there's only one point of retrieval.
I understand, so you can only take from the top, but is there a way to get rid of the top two, like pop it twice? And then grab the element and then put the other two back on?
You can do that. I mean, there are ways, we can certainly do that with using a bunch of pops, retrieve, and then push the original back to the stack.
I'm trying to visualize doing that without losing, the first two values. Cause then, no, I'm saying like, is there a way to do it without, cause to store the variables has to be on the stack, right? So when you pop them, they're gone. And if you get something out in the middle of the stack, you have to put them back, but now you don't have them anymore.
Okay, so let me illustrate, okay, let me combine, actually implement this code in C++ first, so that we understand, what we are talking about, what is push and what is pop, okay? In this case, this is push, we are storing something, and this is pop, which means we are retrieving something. Is that okay? So in terms of terminology, pushing means we are storing something, and then popping means we are retrieving something. Okay, so the term pop, just kind of reminded me to take roll because that's the roll taking word for today. I suppose you can say that I planned today's roll taking activity well because I use a word that I eventually will have to use to remind myself, oh, okay, time to take roll. Okay, so I think you can see already because I just unhide it. The time is not going to work out because it's already past 6 o'clock, so we'll make it 6:15 p.m. But the word is pop, all lowercase, P-O-P. All right, so give it a try now and see if it works. It works? No, it does not. Okay, fine. Okay, I totally tricked myself because it's tart, pop tart. So I was setting a trap, I'm setting a trigger for myself, right? So by the time I talk about pop, I would remember to take roll. But then I also forgot that I wasn't using pop as the word for roll taking. It is what usually associated with pop, which is tart. Okay, they're all too sweet for me, I'm sorry. So are we good with tart? Does it work? Okay. Pop tart. All right, so getting back to all the discussion. So what I'll do is I'm going to write the program. Okay, this is also kind of unplanned because I was not planning to do this, but it's okay. And I'm going to use this window. Zoom in one more time. There we go. And I'll put this in the temp folder. And we'll say this is stack.c. All right, so I'm going to pound define. Okay, fine. I know you guys are much more used to const, unsigned, signed, stack size is 32 and semicolon, and then we have the stack. So the stack is going to be include standard integer.h, and then we have uint8_t stack, and then the size, the number of elements that we want to reserve in this case is stack size. So, and then we have a stack pointer. So that would be a uint8_t that. There we go. So now we have to, I have to define, I'm just trying to think of what I can do to implement this. Okay, I think I know. So void push, okay, so push is a function. You tell me what value you want to push as an 8-bit unsigned integer. So uint8_t, this is x. And then inside push, we would include those two lines, which is starting with decrementing the stack pointer. And then we store to where the stack pointer is pointing to, the value that you're passing to me as a parameter x. And then we have pop. So in this case, pop is going to be returning the value that we are popping. So it has no parameter itself. And then what we do here, okay, I'm just trying to think of whether I want to do it this way or not. Let's do it this way. So I'm combining the two lines into one. So that would become whatever SP is pointing to. So in this case, whether I use a post increment or pre-increment becomes important. Because in this case, I want to use the stack pointer as it is right now and say, what are you pointing to? I'm going to return the content in RAM that the stack pointer is pointing to. After that, it's going to increment the stack pointer. So this one single statement is doing what the other two statements are doing. It's just that this way it's a lot easier when I want to the entire return expression to a single expression itself. Somebody is just trying to join us. Ready. There we go. All right, so are we good so far? Question?
First, the incrementing of the SP or the returning?
What do you think? What do you, okay, so the question is, what are we incrementing on line 14? Are we incrementing the stack pointer or are we incrementing what is pointing to? According to the parentheses, what happens first? SP++ happens first, right? So that means the increment applies to the stack pointer and not what the stack pointer points to. This is also the reason why we needed the parentheses, because without the parentheses, which means if we have asterisk SP++ without any parentheses, then it would actually increment what the stack pointer points to because of the priority of operators. So you have to look up the priority of the reference and then look up the priority of ++. I believe the reference has a higher priority compared to ++. So that's why if we want to increment or post increment the stack pointer, we have to use parentheses in this case to make sure that it is the pointer that we're incrementing and not the content that the pointer pointing to that we are incrementing. All right, so are we good so far? All right, okay. So now we are going to implement the program. And I'm going to use one more function here to say initialize the stack pointer. And this is where it looks a little bit funny because the stack pointer is going to initialize to the address of the last element of the stack, except it is one element past that. Okay. All right, so are we okay with line 19? Do we understand what line 19 is actually doing, what the stack pointer is pointing to? So initially, the stack pointer does not point to the last element of stack. It points to the location right after the last element of stack. And you guys will be going like, but isn't that a bad thing? That to point to a location that is outside of the stack itself? It's not a problem. It is not a problem because when we push we're decrementing the stack pointer first, which means we move the pointer back into where the stack actually owns before we do anything with the address itself. So it's perfectly okay. It is just, you know, a little weird to look at. So what we'll do next? Yes, go ahead.
Just to mention, why couldn't we decrement the pointer afterwards and make it a little cleaner? We just,
You mean why we? You mean this one here?
yeah, I'm saying like, couldn't we do it, set the stack pointer to point to the
That's a-
last element as opposed to one past it? And then we get the value and then decrement.
Oh, you mean why don't we initialize the stack to the very last, the address of the last element?
Yes, stack
And
that
then-
to one, and then
And
in
then
the
reverse
decrement
these
after.
two?
Yeah,
Because you have to reserve first. So this is where things get get totally kind of interesting, okay? Because the stack pointer is basically a bookmark. So imagine that you have a book, a binder, okay, a notebook of some kind. And here's a bookmark. The bookmark is called the stack pointer. So anything that is pointed to by the pointer, in other words, the page where the bookmark is marking, and all the pages after that, meaning, you know, all the locations that are higher than where the stack pointer is pointing to, those are all yours, okay? It is yours, and, you know, the content is guaranteed not to be modified by anyone else. Is that okay? Then the next question is, but what about those pages, you know, that are before the stack pointer, before where the page, where the stack pointer is marking? Those are all open to gremlins to change. And they can come in and change those, the content of those pages anytime they want to, without letting you know. Is that okay? So now the question is, if you want to write down something on your notebook, and you don't want the gremlins to accidentally change the content, what are you gonna do? Are you going to write on that page first and then move the bookmark? Or are you gonna move the bookmark first and say, hey, gremlins, don't touch this page, okay? I'm working on it. And then actually work on it. So which order would you use? Move the bookmark first, reserve that page, then you have all the time in the world to overwrite that page with anything you want. Because until you move that bookmark, that page can be modified by quote unquote gremlins. Yep.
So on line 14, I was just reading up on just a little bit. Couldn't we do asterisk plus FP? Because the
Nope.
incrementing would be before.
Nope.
It's a, no,
Nope. All right, so we are gonna use comments here and specify, you know, what each one means, okay? So you're talking about this, right? Without the what?
without the parentheses, because it's a pre-increment operation as opposed to post.
Okay, and then
No, with the star, but without the parentheses.
over the star without the parentheses.
Yeah,
You mean this?
yes, because the incrementing is a pre-done operation or.
That is a, okay, it's not gonna work for sure, okay? The reason why it's not gonna work is the dereference will most likely is going to apply after you add one to the stack pointer. But what we want to do is to dereference before the stack pointer increments. So no matter, you know, so even with parentheses, this is not going to work. Okay, so let me show you what I mean by that. Okay, so you're basically, it is the same as this, right?
Yeah,
So this is basically the same thing as two different statements. It is the same thing as first incrementing the stack pointer, then you dereference where the stack pointer is pointing to. And that's not what we want to do, because what we want to do in this case is the other way around, which means we are going to, it's hard to express it without using a temporary variable in this case, because we have to retrieve first, and then we increment the stack pointer. And there's no easy way to express that without using a local variable. Let me do this with a local variable, so it will be very clear. So we can use uint_t content, And we can even pre-initialize this to whatever the stack pointer points to. And then, okay, so then we have SP++, okay, or +=1, or whatever you want to specify that, okay? And then in here, we return content. This is what we want to do. Okay. And what you are proposing is not going to do the same thing because you are adding one to the stack pointer first.
Okay, I thought you were wanting it to be the other way around, and that's the reason why we had the parentheses was to push it in front of.
So with the parentheses like this, it is the same thing as what we have here,
Okay,
but there's no easy way to express it, using just you have to use a local variable to store whatever is pointing to first, and then you increment the stack pointer. So there's no easy way to express it without using the post increment in parentheses. Yep.
So I see what you're saying there, but I thought the whole purpose was on thing Jacob on is we wanted to increment the pointer location, like the actual memory, not have it dereferenced, but to increment the memory location and then dereference it.
We want to dereference first, then increment. So, okay, so the question is why? Remember that book and the gremlins? Yes? So the question is, do you want, so let's just say that I'm asking Chris, and say, okay, so can you tell me what is on top of the stack? But once you tell me what is on top of the stack, I don't need that anymore, and we can reclaim that location for something else. So that's my question to Chris. So the question is, what should Chris do? Should he move the bookmark and then read the content of the page that was previously marked by bookmark? Or should he read the content first and then increment the bookmark, move the bookmark to the next page? So if he did it the first way, and move the bookmark first, then the gremlin can get a chance to modify the page that you're supposed to read back to me before you got a chance to read it back to me. So by the time you read it back to me, it's no longer the original content. It is the funky content that the gremlin has put onto that page. So that's why you don't want to move the bookmark until the content where the bookmark is marking is already consumed. Then you can go ahead and move the bookmark and say, hey, gremlins, you can do whatever you want with this page. I'm done with it. Is that okay? So that is the reason why we have these kind of strange ordering. So later on in this semester, I will tell you what the gremlins are representing. But for now, we'll just say there are funky stuff going on in the background. There are gremlins. So anywhere that is below where the stack pointer is pointing to can be changed without your program knowing about it. So you cannot even tell that something has just changed the content at those locations. So the best way to do it is to protect that content, the content on the stack, is to say, I'm not going to move the stack pointer until I know for sure I don't need that location anymore. Are we doing okay so far with that concept? Okay. All right, so getting back to this program, we are going to go back to this notation just because it is a better notation. And this is also the kind of code that you can expect to read when you become a software engineer. Okay, this kind of shorthand is used a lot in programming. All right, so what I'll do here is I'm going to say, okay, let's initialize the stack pointer first, and then I will have it to store and retrieve a few items. And the way we are going to do this is we'll pound include stdio standard io.h, so I can use printf. So we're going to push a few things. Okay, so we're going to push, I don't know, 12 on the stack. We'll push 3 on the stack, and then we'll print whatever we are popping from the stack. So it's %u for unsigned, and then we have to also cast it as an unsigned because the width of the integer is not going to match if I just use pop. So there we go, and then we will push again, and we're going to push, I don't know, let's say 5 this time, and then we'll push again 7 this time, and then we'll pop it twice, and push again. Let's say 11. And then pop again. So we have to make sure that we don't have more pops than we have push at any time. So we have 1, 2, 3, 4 pushes, 5 pushes on the stack. So we have 2 more pops that we need to do before we end the execution of the program. Return 0. Okay, so now I'm asking you, what is the output of this program?
3, 7, 5, 11.
So this pop is going to pop the most recently pushed value, which is the 3. But after you pop the 3, 12 becomes the top of the stack. So we have 12, 5, 7 on the stack. These 2 pops will pop the 7 and the 5. So we have 3, 7, 5. And then we still have 12 and 12 on the stack right now. So we have 12, and then we pushed 11 on the stack. So now we have 12, 11 on the stack. The first pop on the pop on line 37 is going to pop 11, and then we'll pop 12 here from the stack. Okay, so this program is going to be runnable, and I can definitely share this program with all of you. So this way, if you want to get a better understanding of how the stack operates, you can have this program and you can modify that, and just to kind of check out what is going on. You can also go through the debugger and find out what is the exact value of the stack pointer. Where is it pointing to at any point of this entire program? So we'll go gcc-g-o stack C. Okay, and it doesn't like that. Variable modified stack at file scope, line 4. Okay, so maybe it just doesn't like the word stack. So yes, in here. And it only affects the initialization. So we'll see if that's the case. Nope. All right, so what is going on with this program? What is the complaint? Variably modified. Are you referring to stack size?
Yeah.
If that is the case, I'm going to go back to use macros. There we go. Thank you. All right. So that's the order of the output, which I think matched what we said earlier. Are we doing okay so far with this? So, yep.
You have more than one stack for this process.
Every processor. Okay, so that's a very good question. Okay, let me repeat the question first. So the question is there one stack for the entire processor, or are there multiple stacks? Is that your question? That's a very interesting question, because in TTP, let me take it back. With all the programming that we're gonna do with TTP, they're called single-threaded programs. And a single-threaded program can only have one single stack. Okay, so from that one statement, what is it implying? It's implying a lot of things, isn't it? So this is me trying to kind of tell you guys how my brain functions. Okay, so when I say a single-threaded program would use only one stack, the phrase a single-threaded program means there has to be some other programs that are not single-threaded. The opposite of single is multi, right? So we can have multi-threaded programs. So if a single-threaded program only uses one stack, that implies that a multi-threaded program would use multiple stacks. And that would be correct. Each thread has its own stack. So by the time you guys move on to systems programming at Sac-State, okay, because they do have that class, each thread in a multi-threaded program has its own stack, and therefore it can afford to have its own call return thread. But and then each thread has its own stack, so that each one can call and return without interference with each other. Okay, so that's does that kind of answer your question? I know it's not exactly what you're looking for, but a little bit extended, to what you were asking. So since we're only writing single-threaded programs with TTP because we lack the mechanism to perform multi-threading, so that means, yes, we only have one single stack. Is that okay so far? Okay. All right. So now that we kind of understand what a stack is, and the ordering of putting things into it and the ordering of retrieving things out of it, which is basically just summarized by last in, first out. So one thing you can do, okay, which means I'm not going to do it for you, is on each line, tell me what is on the stack. I'll give you the first 3 lines and then you can finish it. So after this, the stack is empty. After this, we have 12 on the stack. After this, we have 12 and 3 on the stack. After this, 3 is retrieved, and we only have 12 left on the stack. So using this particular notation, go ahead and try to finish this program in terms of the notation of what is on the stack after each line executes. Okay, so that means I will share this file with you so that you guys can complete this assignment. Well, it's not an assignment, it's more like a little hands-on experience just to understand how the stack operates. Are we good so far? All right. So now we are going to go back to this note here and say, okay, now that we know how to do all of this in C++, how are we going to do this using TTP? Okay, in the TTP. So the way we're going to do this using the TTP, so we'll just look at these instructions one by one, look at these statements one by one. Remember which register is the stack pointer. I just said that I arbitrarily chose one register and say that you are the stack pointer from here on. Which register are we talking about? Register D, very good. So let's look into how we put something on the stack. So how do we perform SP minus minus using TTP ASM? Which instruction do we use to decrease the content of register D by 1? Yes.
There's a definite operation pretty low down in the opcode table.
Yes. Yep. So decrement D is the one that you want to use. Okay. DEC is the name of the mnemonic, and then you specify register D, and it's going to decrease the integer in register D by 1. Okay. That doesn't sound too hard. So over here, if I make an assumption that register X is one of the registers, we'll just say it's register A, B, or C. Okay. And since we already know that SP is D, do we have an instruction that can do, I'll just take one particular register in this case. Let's just say that X is register A, okay? So which mnemonic is going to get this done? Difference. Asterisk D equals to A. Yes.
Is it, I'm not sure the name of STR, it's like dereference.
It's ST. ST means store. So which 2 registers do we specify?
Oh, like with the letters,
Mhm.
I'm sorry, I didn't hear what you say, but.
So, okay, so there are 2 registers that we need to specify, right? One register to specify, who is the pointer to the location that is going to be changed, and who's applying the value to change that location with. Yes.
It'd be store from D and then whatever register we're going.
It will be ST in parentheses D, comma A.
Yes.
Okay, very good. So that's how we're going to do this. Now, if you're just saying that, I cannot remember all of these instructions when you're just saying it, we'll see that. Okay, later on we'll see. What about popping? Okay, what about forget about the initialization for now, but how about popping? How do we retrieve something from the stack? So we'll start with this one here, okay, which seems to be the reverse of what we saw earlier, right? So what instruction? Let's just say that X is register A again. So how do we do this as a single instruction? Yes. It's load A, comma in parentheses D. Okay, the parentheses are only here as eye candy to emphasize that whatever is parenthesized is dereferenced. That's what the parentheses are for, it's really just eye candy. I could have made the assembly language without the parentheses, but I insisted on the parentheses just so that it's clear to us, what we are dereferencing. Okay, what about the next one? That's C++, and we know that register D is the stack pointer. How do we do this? Increment D, INC is increment, and then you specify it is register D that we are incrementing. Okay, so that's pretty good. I mean, we kind of know what to do with how to push, how to pop. What about this thing over here? How do we initialize the stack pointer? Do you guys remember where is the last location of the entire stack? It's location 255, but this is actually specifying the location right past the end of location 255. What is that? 256, but everything is only 8-bit, right? How do you store, how is 256 stored as an 8-bit number?
0.
Zero, that's it. It looks really odd because we initialize the stack pointer to 0. But that 0 actually is trying to specify location 256, which is 1 byte pass, okay? The address of the 1 byte past the end of where the stack is supposed to end. Yes,
Is this the reason why we subtract down one before we do the, I think it is?
it is consistent with that method of using the stack. That is correct. But it's not the only reason why we use decrement first before we store something to the location.
So, how does the overflow, how does that affect SP? Because you said it, when you reach the max 256, it overflows back down. It shows us a 0.
Yeah.
Does it only show to us and it internally reads it as?
Well, let's run the code and find out, right? I mean, that's the best way to do it, is actually to run the code, find out what it's going to do, okay? So what we'll do is we're going to write a simple program to do just that. So let me do that. And I'm going to change to a different account just because I have a syntax highlighting editor using this account. Okay, so what we'll do is we are going to resemble what the C code is doing, but we'll do it in assembly code. So what I'm going to do is to copy stack.c to stack.btpasm. There we go. And you're seeing all of this highlighting because it is all, they're all syntactically incorrect as a TTP text toy processor ASM, which is assembly file. So we're going to fix a lot of these things. So we'll just go ahead and comment out things that we don't really need to do. To define the stack size, we can actually do it with labels. So we can just say stack size is defined to be exactly 32. Okay, this is something that we have seen before. You guys remember how you tested the absolute value code? You define K1, right, as the value that you're testing. Same thing here. Okay, we're just saying that the symbolic name of stack size is now 32 as an integer. The stack itself does not need to be declared, so this is all implicit. We are using register D as the stack pointer. Once again, this line is irrelevant to us. The pushing and the popping, they're not going to be useful at all. So I'm just going to remove these things here. And the initialization is important, but I will do the initialization in just a little bit. So this is main, okay, but there's no need to declare main because execution always starts from location 0 and move forward from that point on. All right, so we do need to initialize the stack pointer. And as I said earlier, we'll just load 0 into it. But to answer your question, okay, we'll do something a little bit different. So I'm going to say register D is initialized with 255. But since we want the location that is 1 byte pass, that is right after the end of RAM, we're just going to say, let's see what happens when we increment D in this case. Do we have any questions about these two lines? Because location 255 is the actual last location of the stack. The way we want to initialize the stack pointer is we want it to be right after the end of the entire stack. So we just say, hey, we'll just add 1 to it. Is that okay? So this is going to answer your question of what register D would end up as. So we'll get to that part. All right, so we're going to push 12 next. So the push means we have to decrement the stack pointer first, and then we want to store the 3 to where the stack pointer is pointing to. So ideally speaking, this is what we want to do, but we cannot do it. Why can't we do something like this? Which seems to be, that would be pretty handy, but why can't I do it this way? If you look at the opcode table, what is ST telling you? What are the restrictions of the 2 operands of the ST instruction? And I can go take a look too. So we're gonna take a look at the ST instruction.
They both have to be registers.
They both have to be registers. And what gives you that idea that they both have to be registers?
Because X and Y both just specify one of the 4 registers, they're not actual values. The only one that can load an actual external value is LDI.
Exactly, because LDI is the only one that has an operand represented by I, which is the immediate value. This one has Y, but the only thing that can be used to substitute Y is one of the 4 registers. And the same thing about X can only be one of the 4 registers. So that is the restriction, right? So now the question is, well, can't we just change this syntax and we can have an STI, right? And then we'll just say that we can store an immediate into where a register is pointing to. Problem solved. So why can't I do that either? It is impossible to do that. Not because it is not a syntax issue. It's very simple for me to change the assembler to handle new syntax. That's not the problem. What is the problem?
That you can't load out of one area of RAM into another area of the same RAM at the same time.
Exactly.
You just store it in a register first and then put it back in somewhere else.
It has to do with the pathway limitations of the processor. The processor can only have one thing connected to the D port of RAM at any particular time. And there are no internal registers so that you can stash something in that register. So that's why the STI instruction is not even possible because it has to do with the circuit of the processor. It is not a syntax issue. It is an issue with how the processor is designed. Okay, well, how unfortunate, because that means our code is going to look a little bit ugly because we have to, the only way to do this is to use an LDI, put 3 into one of the other registers, like so, and then we change this to this. Does that make sense? Because the only thing you can use with ST would be a register, where the information is coming from. So I just have to use register A and say, hey, register A, I want you to store the value of 3 first, so that you can provide that value when we want to store the 3 into where register D is pointing to. Are we good so far? Right? So now we can look into the next one, which is a pop operation. So I'm not going to print anything. The TTP has no ability to print anything, but we can still exercise the pop operation. Can someone remind me, in terms of the pop operation, what do we need to do first, and then what do we need to do? There are 2 things to do. Yep.
Need to dereference and then decrement.
The reference and then increment.
Dereference, yes.
And then increment. So close enough. That's fine. So we're gonna dereference and say, hey, whatever you're pointing to, stack pointer, I want you to store the content at the location that you're pointing to into register A. So we are retrieving the content into register A. And then we will say increment D. In other words, we put the bookmark onto the next page, because this page, the content of this page is already retrieved. I have no use of this page anymore, so I'm leaving it to the gremlins to play with. Is that okay? All right, so basically the push is gonna look like this, pop is gonna look like this. So the rest of this program is just repeating these patterns over and over again. So I forgot about the push here 12. This is push 3. So this one is supposed to be the 12. I'm just going to be really kind of lazy here and just repeat. I mean, just copy and paste the code. So we have 5. Yes, it would be nice if I have macros in this case, but I don't. So I'm gonna have to redo all of these things. And just be careful about copying and pasting. Oh, the next one is a pop. This is a push. So I do want to finish up this code here, and there is a way to visualize the execution of this program using the tool that I have talked about already before. So that is not supposed to be here. So we have it's 2 like that. Okay, so these are all pops, and then we have another push. I'll fix the syntax error in just a little bit. And then we have 2 more pops. Like so. The return 0 is basically the same as a halt instruction because we have nothing else to do. So that's why we use a halt here. And then for the rest, we just kind of comment out. I don't want to delete those lines because I want you to see what was in the original C code and what assembly code is replacing those C code. So are we doing okay so far with this code, with this program here? I just converted a C program that was used to illustrate pushing and popping into TTP-ASM, and hopefully it would do exactly the same thing. Are we good so far? All right, so let's go ahead and see what's going to happen when we run this code. Oh, there's one more error here. I'm just double checking, making sure that things are looking okay. Just quickly scanning to make sure that I'm not making any mistake here. Okay, there we go. And every program is going to start with a no op instruction, and that has to do with the limitation of if I want to trace the execution of the program so that we have a trace analysis in the assembler, this is what I need to do. Okay, so I'm going to show something that you guys might feel envious about. Yes, go ahead.
You can put labels before the
Hmm?
You can put labels before the no.
Yeah, labels can be anywhere. You can do backward reference, you can do forward reference. It doesn't even matter where you put that label. Yep. All right, so we exit from this program. And then we go to document CISP310 with a spider. Okay, so I'm now cheating. Let me show you what to do without the cheating first, and then I'll show you what kind of convenience you're buying if you use River Spider. Okay, so I'll do it once without using River Spider, and then I'll do it once with River Spider. You might want to jot down the time, which is 6:43 right now. So I'm gonna put the entire program stack.c into the buffer. Okay. Oops. Oh, that won't work. Yes, I just reloaded that. Fine. Oops. That works. Okay, so now we go back to, so this is what we need to do when you want to run the program and trace what is happening as the program runs. So you have to go to the source tab, and then we paste the program here. Okay, well, I want to go from the beginning. Paste this code, and then we go to RAM file. Oh, wait. Okay, that's not it. download, right? So we download CSV, change the name to stack.csv, switch to Logisim. Oops, not this one, but, oh, I just passed it. There we go. And then right click here, go to load image. And then specify that we want to load, what was it again? Stack.csv. Put the program here, right? And then run it. Now, when this is all done, it doesn't really show us how we are pushing and popping. So that means this is not going to be very useful. So instead, what we need to do is something that is a little bit more cumbersome, which means we have to run it on the command line. I know most of you are dreading it. So this is one reason why River Spider is handy. I'll show you why. So the jar file is located at documents, CISP310 processor, Logisim, and then we have to specify the processor file, which is in the same folder. And then we have to specify where the RAM file is, which is in the temp folder, which is my current working directory. So it is just stack.csv. Then we have to specify -tty table, tty table. And then we have to specify redirection to capture the output of this thing when we execute the program. So this is not new, okay? This is the second time I introduced this method. Okay, the first time was a week ago. This is the second time. So now we have a TSV file. We go back to the assembler. We go to trace raw data, and then we go to file, and then we specify import. Then we specify upload. Then we specify where the file is, which is stack.tsv. TSV stands for tab separated values. And let me move this to the other side. Won't open it because that file is not there. Yep,
Was it a CSV?
it should be the TSV. Okay, let me check the command line. Oh, I put it into, yeah, it's supposed to be here. It is here. All right, so maybe I just typed it wrong. Nope, it won't get to the temp folder. Oh. Okay, let's try that one more time. Oh, it's already in the temp folder. So we go to stack.tsv. And then we specify replace current sheet. Okay, this is important. We force it to use tab as a separator. And then we uncheck convert text to numbers, dates, and formulas. Import data. It's going to take a little bit of time. And then we go to the analysis tab to see what is happening. So right here, we can see that we did the LDI D with 255, and that's why register D becomes FF in hexadecimal. And here we add 1 to it. You can see the instruction that's causing this to happen. And then we decrement D in order to push something. So D becomes FF again. We load A with 12. A is now 12. And then we store that to whatever the stack pointer is pointing to, which is location FF. And then we decrement again. And then we, to prepare for the next push operation, we're pushing 3 this time, and so on. Okay, so there's a lot of steps here to find out what is happening, right? Okay, now watch this. Go back to the command line. And this time I have to do it in this particular account. Let's need to change the screen size a little bit. All right. So // what was the command? Submit. And then you specify where the source file is, which is in the temp folder. It's called stack.ttp.asm. And then you press the enter key. Oh, okay. All right, my bad. It's okay, I can fix this. chmod 777 stack dot btpsm. Operation not permitted. All right, so anyway, if it does work, this one single command would replace everything that I just did. It's just running one single command, which means you can make changes to your program really quick and then run the program again and then see the effect of running that program. Yes?
Can you sudo it?
Hmm?
Sudo it?
I suppose I can do that, but it has to do with a permission thing. Sudo is not going to fix the problem. Let me try that one more time. Just give me a second here. I just need to change the permission of the file or change the owner. Yeah, I can see why. I can change the ownership. Okay. And then we'll do the same thing with the other files, CSV, and then also CSV. Okay. It still complains about it. Huh. And, oh, okay, I changed the permission in the wrong direction. So for that, one more time. There we go. All right, so, all right, there we go, it works. It's okay, wait, okay, I know how to fix this one too. Oh, okay, that's fine. All right, so that should work. Give me a second. So it would actually put this code on into the assembler, assemble it, download the RAM file, put the RAM file in the simulator, run it, collect the TSV file, upload the TSV file to the right sheet. And now when I go back to the spreadsheet, it has everything already updated. So yes, it is a time saver. Do you actually need it? No. Is it nice to have it? Yes. Can you run it in Windows? Yes, sort of. Can you run it in Linux and Mac OS? Yes, definitely. So I know you guys have a lot of questions about this, okay? Because it is nice to get it to run. You do have a lab tonight, so let me point you to the lab first. And also the passcode of this lab. So the lab is about stack operation. And it contains instructions, okay? So I would not rush through this lab because it is a part of the instruction. The passcode is LIFO, L-I-F-O, all lowercase. Yes.
What is about a vigorous?
So the spider is a back switch. Back and forth and down. Okay, so it looks like a back part of the window. Okay, but the next is certain utility program. To talk to remotely. So that's how I can help the local square to Google okay. Now, instruction of how to do something.
Yeah. Didn't really want to ask it in class because I thought it would waste time, but so back on when you're putting in the
Mhm.
or creating the stack, popping the stack,